Yeah, g'day, it's Charlie, ZL2CTM. Well, what I want to do today is do a quick little video just to look at some of the initial experiments I've been doing with a Class E amplifier. What I've elected to do is to design it around an IRF 510, not necessarily the best MOSFET, but it's the one that I had the most of here in the shack, and I've been through a few of them already in terms of blowing them up. I must admit, I'm in no way, shape or form an expert in this particular type of amplifier. It's very new to me, and I must admit, I'm sure it's a very good amplifier, but for me and my understanding, it's a little bit like walking on eggs. You're just not quite sure at what point it's going to break through. And like I say, I've had a few devices decide to give up the ghost in playing around with this. Anyway, right, so you remember the first time I played around with a Class E amplifier, I was using this particular paper written by Nathan in WA1HQC, where he introduced, my understanding is, the Class E amplifier, and then went through the derivation of the various formulas to come up with this particular circuit here. So it's a very simple circuit with a switching device, or in this case the MOSFET, in series with the VCC line coming down as an inductor, and then hanging off the drain is a capacitance to earth, and then the series circuit here made up of C2 and L2 with a load. So this was the paper that I used last time. In this particular case, for this amplifier down here, I've elected to have a look at this particular paper here, written by David Gripe, NM0S. If you look online, you'll see a PowerPoint presentation from the same individual here, dated 2011. There are some subtle differences between this paper here and the PowerPoint presentation in some of the formulas that he's used. So just be aware of that one. But anyway, for what I can see, he's taken a I don't want to say a simplified approach, but his formulas seem to be a lot simpler than the ones that were initially taken by Nathan here. So he's referencing Nathan in this particular paper here, and he comes up with the same construction, i.e. the same configuration for the amplifier, but has a different way of calculating the values. So what I'll do, I'll put this aside here, and before going into looking at what I've done here, let's just run through the calculations from David, and then we'll basically go from there. Right, so, and I apologise, this is in 720. If I go up to 1080, it's just the file size is too large to upload. It takes all day. So my preference at the moment is to stick with 720. Anyway, so like I say, this is referencing David Gripe here in his calculations. This is what we're going to be using as the test amplifier setup. The switching device, like I say, that series inductor going up to VCC, the capacitor in parallel, and then these two, this resonant circuit over here of L2 and C2 with our load resistor. A few things from the spec sheet that we'll be needing. The on resistance for this MOSFET here, the IRF 510 when it's full on, is 0.54 ohms, and the output capacitance from the drain to the source is 81 picofarads. So we'll need to take that into consideration too. I'm going to run this on 12 volts. I'm running this on 12 volts because my long-term plan, you sort of just sneaking under there, the main radio itself, I'm going to put into one of those lunch boxes, the slightly larger one, and turn it into a portable radio that I can take away when we go on triathlons and that. So the aim there will be to run it on 12 volts. I'm going to, just as a design number, just work on a power output of 8 watts. And my sort of thinking there is, I never really managed to attain what I desire, so if I aim for 8, then I might be able to get 5. So anyway, this is never going to be a Crow high power amplifier, so let's just run with, well, I'm going to run with 8 watts. Frequency of operation is right in the middle of the 80 meter CW band, which stretches from 3.5 to 3.55, so I'll design this around 3.525 megahertz. Okay, so these figures here, R1, C1, obviously refer to this over here. So we'll start off with using what our load needs to be. So straight out of David's paper, it's 0.32 times VCC squared over power out minus 1.5 times RDS. So basically we've got all our values up here we can now poke in. So plug those values in there. There goes the 8 watts, there goes the 0.54 ohms, 12 volts VCC. We come out at 6.4 ohms. What I'll do in the amplifier down track, as we see down there, I'll use a just a broadband transformer to transform that up. There is another method which you'll see quite often that more the point I have seen more often, and that's to have a pi network here to transform the 50 ohm load to whatever this amplifier needs, in this particular case 6.4 ohms. Okay, so the capacitor across the output of the device, 0.19. Now that value there, that 0.19, you'll see some differences between the earlier and later paper from David. I'm going to stick with the more recent one with 0.19 as the figure. Over 2 pi, our frequency of operation times our newly derived now RL minus C output. So that's the output of the device, which is already sitting at 81 picofarads. So again, plug in our knowns. These are all knowns now, and we come out with 1.26 nanofarads, or in other words 1260 picofarads. Right, C2, so we're now looking at these two values up here. David in his paper talks about making the capacitive reactance of C2 needs to be between 1 to 2 times our load resistance. And we know that XC equals 1 over 2 pi FC. So I'm going to try 10 ohms. So we said it was 6.4 between 1 and 2, so I'm going to run with roughly 10 ohms and see what that comes out with. The paper also talks about it's not too hard and fast, so you can do this a few times, so do it in an iterative form, and then come out with a standard value, as long as it meets this criteria here. So rearranging this formula here, so putting the C up here, moving the XC down, we can then now solve for capacitance, which is 4.5 nanos or 4500 picofarads. I out of my junk box sourced a 47. I used a capacitance meter and came out with 4790 picofarads. So that's what I'm going to use. Okay, so L2, that's the other device that was in series with that capacitor. There goes the formula there. And I will say too that all of this paperwork here I'll put up online, so there's no need to pause this and try and copy things down. It'll all be up on the blog. Again, there's no unknowns there. We know all of this. We've now derived our C2. We know our RL and our frequency of operation, so we can plug all those in, and we come out with 0.945 microhenries. Now I'm going to use a T50-6. I think it's probably a bit of an overkill here for the amplifier given its size, but I sort of erred on the side of having slightly larger devices with the aim of potentially then reducing things as needed. So hence the T50 size toroids. Now using the online calculator, 16 turns on that comes out at 1.02 microhenries. So I could then, to try and get down to that, I could increase the spacing to try and decrease the inductance, or I could run with 15 turns and have 0.9 microhenries, and therefore squeeze things up to try and eke it up to that. In the end I ran with that's a good question actually. What did I do? It was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I ran with 15 turns. Sorry about that. Right, and then it talks about L1. Right, so L1, I covered up. L1 is that inductor that's in series with the drain leading up to VCC. From what I can gather, they talk about this not being overly crucial, this value, so long as the inductance is greater than 10 times L2. So if we just said that L2 is 945, which is pretty close to 1 microhenry, then obviously 10 times would be 10 microhenries. I'm just going to use sort of a standard RFC type approach, so 10 turns on an FT50-43 comes out at 44 microhenries. So if I take this on face value that it's not critical, then that's what I've done. And in fact, I did actually swap out, and we'll look at it close up, zoomed up over here, that RFC with a lower value one, and didn't see any difference. Rightio, so that was for L1. Right, and I just mentioned before that I using a transformer, an FT50-43, that's that one just sitting over here, to transform our 50 ohms back to make it look like 6.4 ohms to the output of the MOSFET. So therefore our turns ratio is the square root of the impedance difference, not difference, sorry, but the ratio comes out at 2.79. So therefore, if I was use 4, 5 and 6 turns, that would give me, given that turns ratio, 11.1, 13.9 or 16.77. So I'm just going to pick on this one here and have it 5 to 14 is pretty close. And that's what we have over here. Right, I then shoved all of those values into LT Spice and simulated it. And I might just try and zoom up on the top traces. Sorry that's a little bit unclear to see, but what I'm tracking here, this green line here is the voltage at the voltage at the drain voltage. The magenta line there, the purple line, is the current through the device. And then just for interest's sake, that red line there is the voltage sitting across load. Now these figures here, I was more interested in the green line here to see what was going to happen here. And I did that because, if you just bear with me, I'll just go back to the original paper from Nathan. Nathan has this table here that looks at, given what you're seeing at the collector, not the collector, sorry, the drain, or across the device, the VCE, in this particular, in his paper, then you can then tweak the value of C1 and C2 in various ways to get the waveform back to more like the ideal, which is, again, excuse me for flicking through this, there's the ideal here, where it's fully off, it's nice and flat, fully on, etc. So that's the reason why I did that, and I was playing around with this value of parallel capacitance here just a little bit to see what impact they had on that. And if I increase that by a couple of hundred picofarads, then I could get this to be quite flat. Anyway, what we see there is just the straight out simulation from the start. The source here, I've just got a 2 1 ohm resistors in parallel. The reason why I did that in the actual circuit was just to give me the ability with the oscilloscope to measure the voltage across that, which is obviously then a function of the current through it. So I could have a look at it to see what this purple waveform here was doing actually on the oscilloscope. And I've now done away with that 100 nanofarad capacitor sitting across that. It's now replaced by a switch, which will just purely short that out to be in line with the test configuration in the two papers. Now the driver itself here, I'm just running it straight out of the signal generator at this point in time. Now I acknowledge that the IRF 510 has a reasonable amount of input capacitance, so yeah, it makes you require a reasonably low impedance driver to be able to stuff sufficient current into that, to, even though it's a voltage controlled device, to get that to switch on nice and hard. But at the moment, just using the SIGGEN seems to work reasonably well. I was playing around with the MC 34151, but for whatever reason I had a few issues with that, and it was causing the device to be conducting pretty hard, irrespective of what the input was from a switching point of view. If I took it out of circuit and I just measured with the oscilloscope the output, then I was getting a nice square wave up to 10 volts for a 12 volt VCC, which was what I was expecting. But like I say, once I put it into the circuit, for whatever reason, it was causing the MOSFET to conduct all the time, which was a bit frustrating. It was causing a few things to overheat. Okay, so let's arc things up. So at the moment we are scoping the voltage across the device, as well as the voltage across the 50 ohm load. We're turned on, we've got 12 volts coming in, 3.525 megahertz drive, square wave at 5 volts peak to peak. And if I was to gear up, we can see here we've got an output 36 millivolts across that 0.1 ohm resistance. So 36 milli should be 0.36 amps coming on in. Right, so up here we can see our yellow trace is the output across the 50 ohm load, so 34 volts peak to peak if you were to count it out, or 12 volts RMS, so just looking just under 3 watts, so not overly high at all. And we can see there with the purple trace there the voltage across the device, and interesting enough we can see there that sort of little peak there jumping up. So it's starting on about 0 and then coming on up and then dropping off again. So if we were to go back to that original paper from Nathan, if I was to, there goes the waveform there, he then talks about the various things you can do to drive that point there more towards the ideal down to 0, which then leads into this table here, where I mentioned before you can do various things. So I reckon I'm sitting in this one here, so the bottom of that peak there, or trough I should say, is pretty well on 0, jumping up and then coming back down again. So if that's the case, then I need to increase both the value of C1 and C2 in the same proportion, and that's what I have sitting down here. So I think you can see that in the view there. So down there is a 470 picofarad capacitor, ungrounded leg. Here goes another 470 puff, and what I'll do now is I'll just key it up, and we can look up on the scope the impact of one at a time, those two devices, and then I'll solder them down for good. So key her on up. So this is the capacitor that's sitting across C1, which is from the drain to earth. You can see there that certainly drops that down quite a bit. We're also seeing, if you look at these two values here, this one here more specifically, the voltage across our load is also dropping off. So starting at 34 volts peak to peak, and then dropping sort of 2 volts there by doing that. Now the other capacitor over here, this capacitor is the one that's in parallel with our value C2, that's that series capacitor. We can also see there that there's also a slight reduction. So let me just go ahead and solder those down. Solder that down there. Solder that down there. Make sure there's nothing short-circuiting, that's pretty good. Let's turn it back on again. And we can see there, so we have indeed flattened things out. Does it look perfect? No, but it's looking better than it was. I did try before the video throwing in even more capacitance, but I just started to just decrease the output. So again, I'm not an expert in this enough to say what's good and what's bad. So any suggestions I have, I'm happy to look at it, and I'll talk about where I want to go next later on. For interest's sake, what I'm also going to do here, I'm just going to play around with the frequency. Because we saw in the calculations that the various values for the inductors and the like, the capacitors are very much driven by the frequency, and that's why, from my understanding is, these amplifiers aren't very good for multi-band radios. They're only really designed for A band. I'll save the battery on that. So yeah, then we'll see that effect here. So 3.525, I'm going to increase at 100 Hertz at a time above and below, and we'll see what the impact is on the waveform. So we'll key it on up. So we're going down in frequency now, so coming down to that's 3 megs. So starting to see more and more power, albeit a bit ugly, but the waveform certainly dropped all off. Come back up now, that's 3.525 where we started, and going out the other end, 4 megs and beyond. So I'd say certainly as the higher the frequency we're getting, our low pass filter there is coming more into play. But you can see there the waveforms are getting further and further away from the ideal Class E waveforms that were initially presented by Nathan in his paper. So there we have it. I'm not quite sure where I want to take this next. Now it's cold, absolutely cold. I don't have enough experience and knowledge with these to say, well, you know, you're only seeing 2 watts on the output because you haven't done X, Y, Z. I don't have enough knowledge on that one. So I think what I do want to do, and I wanted to do this at the very beginning, was play around with a Class C amplifier. So I think I will certainly not pull this apart. I'll just push this off to one side, have a bit of a quiet think about it, maybe do some more reading, and then at the same time play around with a Class C amplifier, probably with a, just debating if it's going to be with a BJT or what, but have a bit of a play around with another style of amplifier. Anyway, I've gone on way longer than I should do. Apologies for just rambling on. Again, this is not a tutorial. This is not how to build a Class C amplifier. This is purely about me just playing around with some design notes from David, using his calculations. He clearly's got more success than I have. Interesting enough, there's a lot of good QRP Class E amps out there in terms of designs using the 7000, the 2N7000 I think it is, MOSFET. Yeah, okay, right. I hope that was useful, otherwise just of interest. I'll say 73s here and continue playing. Cheers all.